Hello and welcome to Mr. Linford's math course. Today we're going to be presenting on the topic of multiplication of radical expressions. In particular, we're going to be reminding ourselves about the multiplication property of radicals. Then we're going to get into how to actually multiply these radical expressions together. And then we're going to look at some very unique cases in which we're going to be multiplying radical expressions that have different indices. So first up, let's remind ourselves of the property that we used when simplifying radical expressions. That property said that if you take a radicand that's being multiplied together for any nth root, you can split up that radicand so that you're taking the radical of each of those factors individually. So rather than taking the root of the products, you can take the product of the roots. So, for example, we have the square root of 45. We said you could break that down into 9 times 5, and then that could break down into the square root of 9 times the square root of 5, and we would get 3 root 5. Well, we want this to also work in the reverse. So the square root of 45 is the same thing as the square root of 9 times the square root of 5. So typically we work in this direction. But now we want to go in reverse. Can we multiply radical expressions together and get a single expression back? So using this idea, let's take a look at this example. We have one expression times another expression. We're multiplying 2x times the square root of y times negative 7 times the square root of x times y. So let's go ahead and try to multiply these things together. Now, keep in mind, this is all just a giant multiplication problem. 2 times x times the square root of y times negative 7 times the square root of xy. These are all just a bunch of things multiplied together, so I'm going to use that associative property and I'm going to rearrange these terms. Let's multiply the 2 and the negative 7. And the x. And then let's multiply the root y and the root xy. So I've grouped together everything that wasn't in the radical on one side and all the radical terms on the other. So we end up with, let's see, that's negative 14x. And then we are going to go ahead and we're going to use the multiplication property to recombine these. We said if you are taking the radicals and they're the same index, they're both square roots, and you're multiplying them together, you can actually multiply those radicands back together. That's what this is saying. The property told us that if you're multiplying the same index, you're taking the same root, and you're multiplying these together, you can actually just multiply the indices together. I'm sorry, not the indices, the radicands. Too many vocab words in this section. All right, so we have negative 14x and the square root of x, y squared. What we've done is we've multiplied the y's together. Now, when you do multiplication with radicals, it's very likely that you can simplify the radical down further. Because when you're multiplying, you've actually increased the radical, so you're likely to be closer to actually being able to simplify it down. And in this case, we can. We get negative 14x. Well, the square root of y squared is just y. And we're left with the root x on the inside. So take a minute, pause the video, make sure you're comfortable with all of these steps that we just did, especially these steps where we've gone and we've remultiplied the radicands together. Now let's keep on this idea of multiplication, but this time let's increase the size of one of the terms. Here, this is kind of like a binomial. I'm multiplying one thing by two different quantities. So how do we go about doing this? Pause the video, take a minute, think to yourself, how might we go about performing this multiplication? We're taking one quantity and multiplying it to two others. Come up with a little hypothesis on what you're thinking and try to test it out. Then come back to the video and see what we come up with. Well, hopefully you've recognized that when we're multiplying one quantity to two other quantities in a set of parentheses or multiple quantities, we can essentially distribute that value through. So that's what we're going to do right here. We're going to use the distributive property to multiply 5 root 5 times 2 root 5. And then we're also going to multiply 5 root 5 to the 2. And let's see what we get. If we multiply the things on the outside, we get 5 times 2 is 10. And then we get root 5 times root 5 is root 25. Minus, so let's multiply the things on the outside. 5 and 2 make 10. And then there's no radical so to combine the root 5 with, so we'll just leave it. So here's our answer. We have 10 times the square root of 25 minus 10 times the square root of 5. Now go through and check, and we'll very obviously see this radical can simplify. So we end up with 10 times 5 minus 10 root 5. Notice the square root of 25 is 5, so that actually was able to break down. So we end up with 50 minus 10 root 5. Can we go and combine these anymore? No, we can't, because they're not like radicals. So don't worry about that. We've gone through and we've simplified this expression down. We've performed multiplication on it. So this is very similar to work we've done before. All we did was we relied on the distributive property. When you're trying to multiply a quantity to several quantities in a set of parentheses, just use the distribution property. With that idea in mind, now let's up it to where we have two quantities times another two quantities. This should remind you of multiplying binomials, right? Think back to when we had stuff like 2x plus 1 times 3x minus 5, whatever. When we're multiplying two binomials, we're kind of doing the same idea. Now what we're going to have to do is we are going to take this and distribute the whole thing through to both terms. That's going to be really tedious and messy. Can you think about another technique we might be able to do? Instead of distributing a whole quantity through, can you think of something else we've done in the past that might help? Well, hopefully you're thinking back to box method. Box method multiplication is going to be great for this type of problem. So let's set it up where we have the two quantities as columns and two quantities as the rows. So let's take root 5 and 3 root 2. And let's make the columns here be 2 root 5 and negative root 2. Let's hope I get enough space here. All right, so we're going to treat this just like we did when multiplying polynomials together, right? Because again, it was just distribution, and that's all that this box method does is distribution. So let's go through and let me try to color code each one of these. Let's multiply 2 root 5 and root 5 together. We're going to get 2, and root 5 times root 5 is root 25. I'll hold off on simplifying for a minute. So we got 2 root 25. And then for the next one, we're going to multiply negative root 2 and root 5. So we're going to get negative root 2 times 5 is 10. So we have negative root 10. Okay. Now let's multiply 3 root 2 and 2 root 5 together. Well, the 3 and the 2 combine to make 6, and the 2 and the 5 make root 10. And then the very last problem to multiply is negative root 2 and 3 root 2. So we're going to end up with negative 3. The negative and 3 can make a negative 3. Root 2 times root 2 is root 4. Again, I'm holding off on all simplifying. Pause the video, take a minute, make sure that you're able to see how each of these quantities were multiplied together. What we're going to do now is go through and actually try to simplify down any of these radicals that can be broken down further. The first one I see is right here. The square root of 25, that can break down, right? So let's say that the square root of 25 is really 2 times 5. And what is 2 times 5? Well, that's just 10. And then I see another thing that can break down, the square root of 4. All right, so let's break the square root of 4 down. The square root of 4 is just 2. So what's negative 3 times 2? Well, that's just negative 6. So what do we have for our final answer? When we multiply all of this together, we got a 10. We have, well, remember in box method, the like terms are on the diagonal. So we have a 6 root 10 and a negative root 10. That's a positive 5 root 10. And then the last term we had was a negative 6. Well, if we combine some like terms here, the 10 and the negative 6 make 4. And we can't really do anything with the 5 root 10 because it's a radical. It's not going to combine with the number. And there you go. That's our final answer. I really like these problems because it really requires us to use all of the techniques we've been doing so far. From when we're multiplying radicals, we actually have to use the multiplication property that we know about. We then have to add like radicals together, like terms together, and we have to go ahead and actually simplify down some radicals some new radicals that we get. So really we're using pretty much all of the techniques that we've had before. If you're struggling on any of those former techniques, make sure you go back in those videos, check over what you're unsure about, ask me some questions, send me some emails, okay? I'm happy to help out. But this idea of the box method is going to be incredibly helpful in our method for solving these multiplication problems. If we weren't to do the box method, I'm going to show you really quick for this problem. You'll see how messy it is because this is a two-termed problem times a three-termed expression. So a two-termed expression times a three-termed expression, this is going to be really messy. But I'll show you what happens if we were to take this and distribute it through to each of these three terms. We would end up with, I'm going to need a lot of space here, 6 times 2 root x plus root y minus root x times 2 root x plus root y plus 8 root y times 2 root x plus root y. Then you'd have to go and distribute each thing through again individually to get, let's see, 6 times 2 is 12 root x plus 6 root y minus 2 times root x squared minus root xy. And then you'd have to distribute the 8 root y through to get a 16 root xy plus 8 root y squared. Then you'd have to simplify anything that can be simplified. Looks like this and this can break down. So you get a 12 root x plus 6 root y minus 2, well that's just x, minus root xy plus 16 root xy plus 8, well that just simplifies to a y, the square root of y squared. And then you got to find any like radicals to combine. Well, these are like, so I guess I could combine those. We have a, what's this, a 12 root x plus 6 root y minus 2x plus 15 root xy plus 8y. So this problem, you might be saying to yourself, hey, that doesn't look that bad. And there are some people, I've had a number of students that love the distribution method. They like having everything laid out like this. For them, it makes sense. To me, it just looks like a giant mess. I'm going through it pretty quickly. I've worked out this problem before. For me, it's fine to do, but I just love the box method. Something about the box method is just really nice. It keeps everything so organized. You can see where your like terms are, and it really lets you work with just one thing at a time. So let's take a minute to go back through this problem, but instead, let's organize the box technique where we just distribute each thing through one at a time. Again, you choose which method you like. If you're a distribution person, then just stick with distribution. That's fine. But if you're kind of unsure or you're not the most organized with your work, I would recommend this box technique. So I'm going to set 2 of these up for the rows, and let me set the columns up. 6, negative root x, and then 8 root y. Students still ask me, does it matter what are the columns and what are the rows? Could I have made this where we have 6 minus root x and plus 8 root y as the rows instead of the columns? Yes, of course. As long as you're sticking with the same terms, you're good. So let's start the first part off. Let's take 6 times 2 root x. That's going to give us 12 root x. Okay, now let's move to the next part where we have 2 root x times negative root x. Let's see, 2 and negative makes negative 2, and root x times x is root x squared. Again, I'm going to hold off on simplifying for just a minute. Then let's multiply, I'll do green, 2 root x and 8 root y. That's going to be 2 times 8 is 16, and root x times root y is just root xy. Now, let's go and do the second row. We have a root y and a negative root x here. Let me actually change this to green. Sorry, I'm a stickler for color coding. Now let's go into the second row, and let's multiply together the root y and the 6 to get a 6 root y. And you know what? Let me change up the color. I'm going to use yellow this time. 6 root y. Sorry, I'm a stickler for color coding. And then let's go ahead and let's multiply the root y and the negative root x together. Oops. And let's get a negative root xy. And then the very last terms we're going to multiply together are the 8 root y and the root y. So why don't I get, well, let's try a color I haven't tried before. Let's get this. So we have 8, and root y times root y is root y squared, because y times y is y squared. Okay, so we've gone through, we've done all of the multiplication, we've distributed each thing through individually. What we need to do now is, I think it's first a good idea to see what can simplify down, all right? What can break down? First, I'm noticing, hey, I got a square root of y squared. That can very obviously be broken down. So that's just going to be, the square root of y squared is just y. So we have the 8y there. You should also notice that the square root of x squared, that can be broken down. That can be broken down. So let's go through and change the square root of x squared to just x. Now, a quick scan of the rest of these shows that nothing else can really break down. However, we can now look for some like terms. Remember, like terms occur on the diagonal. Well, those aren't any like terms, so don't worry about those. But hey, these are, so we can go ahead and combine them. So our final answer when we do this multiplication, we got a 12 root x. We have a 6 root y. We have a negative 2x. When we combine our like terms, we get a 15 root xy. And we have, for the final one, an 8y. And there's our final answer. I like this with the box method. It's less writing. It's less cramming everything together. We can very clearly see and work with each thing one at a time, and we get our final solution. So, if you have any questions about this, please pause the video, try to work through it, work with which method you like. Again, if you're not the most organized writer, and if you don't have your work organized the best, try the box method, see if it helps. Now we're going to try a problem where we're taking a radical that's to a certain root, and we're going to raise it to an exponent. So in this case, we have the fifth root of 13x squared y raised to the fifth power. So if I thought about this in expanded form, this idea of raising something to the fifth power, that's the same as saying, okay, let's take the fifth root of 13x squared y times the fifth root of 13x squared y times the fifth root of 13x squared y. Oh boy, let's see, the fifth root of 13x squared y. And one more, the fifth root of 13x squared y. So we've gone through and we've multiplied 5 of these things together. What do you think we get when I have a fifth root raised to the fifth power, right? I have something, I have 1/5, another fifth, another fifth, another, and another. Any guesses what we might get? Well, I'm sure you're probably pretty certain of it, but if we wanted to, we could do the long, drawn-out work and kind of prove what we would get. I have 5 13s being multiplied together, so that's 13 to the fifth power. And then I have x squared times itself 5 times, so that's x to the 10th power. And then I have y times itself 5 times, that's y to the 5th power. All right, well, if I split this up to simplify, I could take the fifth root of each of the terms individually, and let's see what I would get. The fifth root of 13 to the fifth is just 13. The fifth root of x to the 10th, I can make 2 groups of 5, so that's x squared. And the fifth root of y to the 5th is just y. Hey, what do you know? It's the radicand we had to start with. So this should be fairly obvious that when you're going and you're taking something to an exponent that's the same index, they just cancel out, and you're left with the radicand, okay? So for example, let me do a quick little example on the side here. If we had, let's say, the 7th root of 21x to the 5th, and I raise that to the 7th power, I don't need to do any work. I just know that these are going to cancel out, and I have 21x to the 5th. I have whatever that radicand is. So we might want to put a little note to ourselves here that the index cancels with the same exponent. So you don't need to go through and show all of this work, but it just helps us to see what's going on. Now, let's try to get into some more complicated problems. In this situation, what we're going to do is try to figure out what happens when the indices are different. In all of the previous problems, the indices were the same, right? And that's really what our multiplication property of radicals says. If you want to combine, they must be of the same index. That was key. They had to be of the same index. So if they're not of the same index, we might say that we actually can't perform this multiplication. It can't be done. We must have a different, we need to have a different solution, or we need to say there is no solution. Well, there's a way of getting around this, and it's very clever. If you think back to when we work with fractions and we're working with rational expressions. Remember how we would add things together like 2/3 plus 1/4? We used to say you can't add those because they have different denominators. And back in elementary school, we learned how to make them the same denominator. So we might, for example, change this. We would multiply the top and the bottom by 4 to get 8 over 12. And this by 3 over 3 to get 3 over 12. We said 2/3 and 8/12, they're the same thing. 1/4 and 3/12, those are the same thing as well. We said they're not different. They're just not simplified. We just change them around. They're the same proportion. They're the same fraction, right? One's just a simplified version of the other. Let's use that framework, that same idea, to try to work around these different indices. So, for the first part, I have a 3 as an index, so I'm taking the cube root of 5. And then the other one, I have a 4 as the index, so the 4th root of 5. Well, if we could change the indices, if we could change the index for each one, it might be able to get combined together. But how do we change the index without changing this whole problem, right? I mean, why can't I just say, oh, all of a sudden this is just the 4th root of 5. There, I changed the index. Well, no, I mean, these aren't the same thing. We're going to need to change it so that way the cube root of 5 is the same as our new index. So first ask yourself, what does 3 and 4 have in common? What values, what multiples of 3 and 4 are in common? Well, the first one that comes to mind for me is 12. So could I turn this 3 root 5 into something of root 12 and have it be equivalent, have them be the exact same thing? So if I take the cube root of 5, if I wanted to get it to be of the 12th root, I would have to raise 5 to some exponent. Right now I have 5 to the 1st power, and I've cubed it. What exponent would I need on 5 if I'm going to take it to the 12th power? Well, if I multiplied 3 by 4 to get 12, I better multiply 1 by 4. So in this problem, let me try to clean it up. If I want the 12th root of 5, I better make it the 12th root of 5 to the 4th. The 12th root of 5 to the 4th is the same thing as the 3rd root of 5, or the cube root of 5. They're the exact same thing, because 4 and 12 are in the same proportion as 1 and 3. Okay? Now let's take a look at the 4th root of 5. I want this 4 to turn into a 12. I want this to be the same index as this. To get that, I would have to multiply the index by 3. So that means I better raise 5 to the 3rd power. So if I had the 3rd power of 12, of the 12th root of 5 to the 3rd, I should say, that's in the same proportion as the 4th root of 5 to the 1st. Hopefully you're seeing how these proportions work. It's like 1/4 here and 3/12. It's also like 1/3 and 4/12 over here. So hopefully you're seeing these proportions. If you have questions, let me know. I could get more in depth of to why this is working, and I can make a video about that, but I don't want to take up too much time. Let me know if you have questions or if this idea of proportions isn't making sense. We can break it down a little further. But the idea here is that you raise the exponent to some amount, so that way the index and the exponent are in the same proportion as before, but now they're the same for the two problems, or for the two expressions. So we can go ahead and multiply these now. We have the 12th root of 5 to the 4th times 5 to the 3rd. So that should be the 12th root of 5 to the 7th power, if we just go ahead and add those exponents. So, with this said, I hope you're seeing the process that we're using for this. I would say that this process, if we're going to break it down step by step, we should say that we first need to determine the common multiple of the indices. So determine the common multiple of the indices. Here was 3 and 4, so a common multiple could be 12. That's actually the least common multiple, but you don't need the least common multiple. It could be any common multiple, like 24 or 36, etc. So determine the common multiple for the indices. Then what you're going to do is you're going to raise the radicand exponent and change the index to be in the same proportion. Now, with them in the same proportion, we're able to go ahead and multiply. Multiply as normal. Now, one trick that you can use for going through and actually trying to come up with a common multiple is actually just taking the indices of each one and raising your exponents to those indices. What I mean by that is, in this problem we have a cube and a square root. So what I would do for the first one is I would take 7 and I'd raise it to the second power, and I'd take 3 times 2. And then for the square root of 2, I'd raise it to the third power and take 2 times 3. So here we would end up with the 6th root of 7 squared, which is 49, times the 6th root of 2 cubed, which is 8. And then we could go ahead and actually multiply that together. 49 times 8 is going to be, so that's the 6th root of 392. So here, this is just a quick and easy technique of just actually multiplying each index by each other, and that guarantees you a common multiple. Is it the least common multiple? No, not every time, but it's a quick way of getting a common multiple. Now, to be fair, we should check to see if we can break down 392. So I'm going to use the prime factor decomposition, and let's see if we can break that down. So 392 divided by 2 is 196. That divided by 2 is going to be 98. That divided by 2 is going to be 49. And that breaks down into 7 and 7. So let's see. Can I take the 6th root of, 2 times 2 times 2 times 7 times 7. Does this simplify at all? Well, no, because I would need a group of 6 terms. I only have 3 2s and 2 7s. I would need 6 7s at least, or 6 2s at least. So this isn't going to simplify down. So here is our final answer, the sixth root of 392. Now let's go through and try some practice problems out. We have the cube root of y times the square root of y. Similar to before, I'm going to just multiply the indices by each other. So we can end up with 3 times 2. And if I do that, I have to raise 2 to the second power. And then I'm going to take 2 times 3 for the second radical. And if I do this, I have to raise y to the third power. That's a terrible 3. So we end up with the sixth root of y squared and the sixth root of y cubed. And again, you can check to make sure that these are in the same proportion. This was a 1 to 3. That 2 to 6 is the same as 1 to 3. This was in a 1 to 2 ratio. This is in a 3 to 6 ratio. Yeah, that's 1 to 2. So it works. They're still in the same proportions. So we can go ahead and multiply these together now that they're the same index. So we get the sixth root of y to the fifth power. And we know we can't break that down any further. Let's try the next one. Pause the video and try to see if you can multiply together the square root of 11 with the sixth root of the sixth root of 2. Well, going through this problem, we're going to do the same technique as before, and I'm going to take the square root of 11 and multiply it by 6, and I'm going to raise 11 to the sixth power. Then I'm going to take the sixth root of 2 and multiply it by 2, and if I do that, I got to raise 2 to the second power. So we should end up with the 12th root of 11 to the sixth times the 12th root of, 2 to the second power is 4. And again, you can go and make sure that these are in the same proportions, right? Here I have essentially, here we had a 1 to 6 ratio. Here it was a 2 to 12 ratio, which is the same thing. Here I had a 1 to 2 ratio, and now I have a 6 to 12 ratio. Again, same thing. We can go ahead and actually perform this multiplication. 12th root of, 11 to the sixth power, that's a big number, times 4. Oh boy, that's 7086244. Let's throw some commas in there. I am not concerned about breaking that radical down. That is, I'm sure it could probably be simplified, but you know what? I don't want to have this video go on for an hour. So we're fine leaving it when it's exceptionally large of a number like that. All right, now let's go ahead, try out some practice problems on your own, see how you're doing with this idea of multiplying the radicals either using distribution or box method, and see how you're doing with this idea of different indices, trying to keep them in the same proportional relationship. If you have any questions about that, or if you're really confused, feel free to let me know. Shoot me an email. My email is klinford, that's KLINFORD, at wccnet.edu. And feel free to let me know in the comment section what you thought of the video. If you have any questions or comments, just let me know. Until next time, take care.